Welcome back. This is the last video in our Chapter 5 series, and it deals with Section 5.6, motion with a constant force. So this can be summed up in basically one statement. If the net force on an object is constant, the acceleration is constant. Okay, you probably already figured that out, but it's good to put that right out there. And let's look at a problem that uses that. So here's an example. We have a block of mass m slides down a smooth, frictionless plane with incline theta. Two things to do. Find the acceleration of the block along the plane. And we want to find the normal force of the plane on the block. Okay, so as always, you draw a diagram, then you draw a free body diagram. Okay, diagram showing the situation, free body diagram, you're isolating the object of interest. If necessary, you break that object of interest into parts if it has multiple components, and you could draw a free body diagram for each one of those. The free body diagram, the diagram is free from, the object is free from its surroundings, and the only thing you put on it are the forces that are acting on it. So here's our diagram. All right, so in the diagram, we have a ramp. I have that there. We have a well, that's not going to work so well. I'm just going to freehand that. We have a, what is it, a block? Okay. So we have a block here, and the block has a couple forces acting on it. First of all, let's make this clear that this is our theta right here. All right. So the first thing you always think is weight. So you have the weight, which is mg. Right. It's always acting toward the center of the earth. The normal force, though, is always acting normal or perpendicular to the surface of interest. So the normal is acting this way. So the normal and the weight, when you're on an incline, are not acting in the same direction. All right, now, if we were to take this, go out here, note that this angle right here is also theta. And I'll let you work out the geometry if you need to prove that to yourself. So free body diagram of this guy. Okay, I'm going to, here's how I'm going to set up my coordinate system. I'm going to make an x-axis that's parallel. Basically, I'm going to make this ramp my x-axis. And I'm going to make my y-axis perpendicular to that. Like that. Okay, so this is my x, this is my y. So here, right here is my my block, considered a point mass. And here I have my normal. And here I have mg. And this is theta. So this component is mg minus mg cosine theta. Okay, according to my coordinate system, that's in the minus y direction. And this component of the weight going this way in the x direction is a positive mg sine theta. All right, so now for we're going to find the acceleration of the block along the plane. That's the x direction. So for A, we're going to sum the forces in the x direction. That's going to be mass times acceleration in the x direction. So the sum of the forces in the x direction is just one. There's mg sine of theta, and that equals mass times the acceleration in the x direction. The mass is the same on each side, so we can get rid of that. So ax is just g sine theta. B asked us to find the normal force of the plane on the block. That's in the y direction in my coordinate system as I defined it. So all I have to do is the sum of the forces in the y direction equals mass times acceleration in the y direction. All right, so the thing is, there's no acceleration in the y direction. It's sliding on that plane. It's not going above it or below it. So there's no acceleration in the y direction. So this is 0. So the sum of the forces is going to equal 0. So the sum of the forces in the y direction, you have n in the positive y direction. And then in negative y direction, you have mg cosine of theta, with all that equal to 0. So you end up with the normal force equals mg cosine theta. And those are our two solutions. All right? By choosing the coordinate system like this, we only had an acceleration in the x direction. Right? So that made it easier to do. All right. So all right, that's it for today, and we'll see you Monday. Bye-bye.